Hello and welcome. In this video I'll be covering section 5.6, which is over the applications and models for growth and decay, as well as compound interest. My goal for you by the end of the video is to be able to solve applied problems involving exponential growth and exponential decay, to be able to solve applied problems involving compound interest, and to be able to find models involving exponential functions and logarithmic functions. So with exponential growth and exponential decay, each of them have kind of this root parent function, if you want to think of it that way, that's really kind of more of a fill-in-the-blank idea. So in this case, notice we have some p of t being equal to p sub 0 multiplied with e to a power of k times t, where each of those variables has something that it represents. So the p sub 0, or p with subscript 0, would basically essentially represent our population at time 0. The e is just that natural number, the 2.718. The p of t, or the p that's on the other side of the equal sign by itself, that would be the population in the end, or at some specific time t, which t is representing the amount of time. K is either your growth or decay rate, so that's really like, I guess, what could be considered your exponential rate of growth. And if k happens to be positive, we know it would be a growth model. If k came back negative or less than 0, then it would be a decay model. And that rate unit does need to be in the same unit as which the time unit is. So if our time was in terms of years, I would need to make sure that my rate was also in a per year idea. So we always do have to be mindful of, do the actual units match up the way that they are supposed to. As far as how these models look, a growth model is essentially something that should grow as we're going from left to right. So that would be like a normal exponential function being graphed, whereas a decay model, notice, is one that would be falling down the page or decreasing the entire time. Hence why it would actually look like it's a reflection over the y-axis, or that exponent would have to have a negative value in front, which would accomplish that flip over the y-axis. So again, this is just to kind of give a little visual of what a graph for each of these should look like when it's all said and done. So we'll go ahead and jump into our first example here. So this one happens to be a population growth problem. It gives us essentially when our time of 0 is, so this year of 2014 is essentially telling us, by giving us the initial value there, that's going to be when time is 0. So in this scenario, I know that the p sub 0 for this problem is going to be that 25.8 million. And then it does give us a growth rate, but as a percentage. So realize when things are written in percent format, our first instinct should be that is a per 100 number, which basically means I need to move the decimal 2 places to the left, because that's what dividing by 100 would accomplish, and that would actually be the number I want to use. So instead of thinking of it as a 2.19, I need to actually utilize a 0.0219 whenever I end up using that. So this is going to have 4 parts. It's going to want us to actually find what that growth function is, then actually graph it, and then we can use the function then to estimate populations at specific times. So in 2018, if we think of 2014 being a time of 0, 2015 then would be 1, and so on and so forth. So 2 for 2016, 3 for 2017, and 4 for 2018. Or the faster way we could have done that is just subtract 2014 from 2018. And we know that for part C, we're going to just basically plug in a t value of 4 and solve for it. Then the very last one's going to be actually solving an exponential set equal to a number. So this will be like the p of t number, or the number that I'll set the function equal to, which then means I'll have to solve for the time. So the when, anytime you see a keyword like when, that's ultimately going to let you kind of know, okay, I should be isolating t somehow, some way when I set up that equation. So let's go ahead and jump into at least the first part. Part A just wants us to find the exponential growth function. So as mentioned before, our template is p of t equaling p sub 0 times e to some kt, where that k is our growth rate, which in this case is going to be that number I mentioned earlier, 0.0219. T is just going to be our time, and the p sub 0, that should be the number that they gave us. So as far as the finding of the actual function, it's really just plugging those two numbers into the correct spots. So in this case, 25.8, and then e to a 0.0219 t. And notice, because that is a positive, even though it's a small number, because it's a positive number, that still creates the idea of this being a growth model. Now, part B of this problem will want us to actually create a graph for this, at least on a grid that's been provided. So again, just to remind us of what the function was, it was p of t equaling that 25.8 e to the 0.0219 t. So ultimately what we could do is just create a t-chart and maybe plug in some of the numbers that we have. So I'm expecting this to kind of flatten on the left pretty quick, so I might be able to just get away with -10 being the smallest number to plug in. Plugging in 0, we should already know, because that's the time 0, so that should be the 25.8 million. So I'm going to go ahead and just fill that one in, since we should know that one. And then maybe just go kind of each tick mark out and just see how far we really have to go for each of these lines. But hopefully by the time I get to 30, maybe 40, we'd have enough points that we'd feel pretty confident that we'd be able to come up with it. So without further ado, let's go ahead and try and figure out what each of those would equal. So if I plug in -10, looks like that gives me a 20.7. If I plug in +10, gives me a 32. Looks like 0.1. Plug in 20. Again, I'm just replacing each of the t's, or the t every single time with this. So this one comes out approximately 40. So this is 39.97. So I'll just call that 40. Again, it's not perfect, but it should at least get us some points in the ballpark. Plug in 30, it gets me to 49.7. So it looks like I might need to go a little bit further. Plug in 40. After all, we top out up at 100. So basically I'm just going to go until I finally get a number that's above 100. We'll just call that 62. 61.95 was what that one turned into. And do one more at 50. And I'm going to guess this one's probably going to be pretty big. 77. Well, never mind. 60 finally was the magic number. So 60, if I were to somehow add that into this table, 60 is going to be paired with 96. I'll just write it as an ordered pair. So going through and plotting these points, I've got -10 was up at 20.7. Might need to do -20 since that still was relatively high on this grid. 0 was at 25.8, so just put that about halfway. 10 is at 32. 20 was at 40-ish. 30 was up at 50-ish. 40 was up at 62, so a little bit of that growth starting to happen. It's starting to go up a little bit faster. 50 was up at 77. And 60 was all the way up at 96. So maybe let's go ahead and figure out a couple of extra numbers. Plug in -20. That one comes out 16, so negative. -20 was with 16-ish. negative 30 at 13-ish. That should give us enough points. So plot those last two, negative 20 up at 16, and negative 30 at 13. So it's got this growth kind of thing happening here. Hard to try and draw it nice and smooth. There we go. So we could use that to our advantage to maybe approximate some of the times when it equals a specific population, or even at a specific time what the approximate population could be. That's what this would really be modeling for us. Next part of this problem just wants us to estimate the population in 2018. So again, 2018, if 2014 was time 0, then 2018 would be when time is 4. So that basically is going to be take my equation, which was P of t equaling the 25.8 e to the 0.0219 t. So really it would just be figure out what is P of 4, which will be 25.8 times e to the 0.0219 times 4. And if I were to figure that out, it looks like this will turn into approximately 28.2 . And again, we're talking in millions, so I'd want to make sure that I'm saying it's 28.2 million, because just saying 28.2 people, that would definitely be a significant decline, not an increase. So this is something that we would want to make sure that we're including our labels here of million in order for that to happen. And if we look at where time of 4 would be, it would be approximately here on our graph. It seems like that fact that that came back close to 30 but less than it, at least our graph kind of verifies that for us. Now on to the last part of this problem, which is more than likely the more difficult of the 4 parts. But this one now, it actually wants us to set it equal to a specific value and solve for a time. So once again, we'll go ahead and get that expression back onto the screen. So this, remember, was the P of t being equal to the 25.8 e to the 0.0219 t. So this one will want us to actually specifically set this equal to 40 million, or tell me when the result is 40 million. So that's really like the P of t portion. So it's going to be by itself, and I'll actually try and solve for what the t is up in the exponent area. So if I go ahead and do that setup, it's going to be now 40 is equal to that 25.8 e to the 0.0219 t. So to start the solving process, I would take the coefficient that's already out in the open and get it at least to the other side. So 25.8 will be what I divide. That way it cancels in front of the e. And if I go ahead and do that in the calculator, that's going to simplify to a 1.55 approximately. And that would still equal the now just e to the 0.0219 t. So to cancel that e, kind of think in terms of inverse operations. If e was inside of a natural log, then it would cancel out, leaving just the exponent. So what I want to do then is take advantage of that and actually take the natural log of both sides. That way I actually can say, well, the natural log and the e should cancel out and leave just the exponent. So I'm going to go ahead and just physically say, well, the natural log and the e are going to cancel. So really, ultimately, the only thing that would be left is this 0.0219 t. Well, if I'm trying to get t by itself, really I'll just divide by that number. So I'm going to kind of combine those two ideas into one step, because I already had the left side as it was going to simplify to anyway. So I've got the natural log of 1.55 that's going to need to divide by the 0.0219. And if I go ahead and, in this case, solve for what that t equals, the natural log of 1.55, when I divide by 0.0219, comes out just a little bit more than 20, so I'm going to go ahead and say that that's 20 years. Now this question actually was saying a when concept though, so that's more of a like what actual year was it? So that's when the t equaling 0, which remember the t equaling 0 was this original number, 2014. So if I said 20 years later, when is that? So the actual when for this would have been the year of 2034. Again, mainly just doing the original year 2014 and adding the 20 to it to get the actual when for this problem. The next type of model that we have that still deals with this concept of exponential growth would be an interest compounded continuously. So what that really means is when interest is being paid upon interest, we call that the compound idea or compound interest. So in this scenario, the P of 0 is, instead of representing a population, it's actually standing for how much money you're investing or how much money you're starting with. And then the interest rate is going to be K, or sometimes this is written using an R instead of a K. Does not really matter. It's just a variable representing the interest rate. Does need to be as a decimal, just like we did before. So if it's ever presented as a percent, convert it to a decimal right off the bat. And if it's compounded continuously, we're going to end up having that base of E. So once again, each of the variables still has a general idea. It's just instead of calling the K the growth rate, it actually is now the interest rate. But I still am having the same model of P of T being equal to our initial investment times e to the KT. So it's still that same basic formatting, it's just now we're specifically talking in terms of money, and the t value does also have to be presented in a time unit of years. And the interest rate also needs to be a per year investment, so it would need to say something, or just say the interest rate. If it doesn't imply anything, then that would be in terms of whatever the years were. So let's go ahead and transition into an application of those notes, which is the next example. So this one, notice it's giving us a couple of values in the problem. So the first thing we'll want to do is just figure out what do we have. So it does say that 2,000 is the amount I'm investing, so that would be the P sub 0 at some interest rate K, so it seems like it's not giving me that value. Compounded continuously, that statement of this technically is telling me that the base is an E on my exponential. Then it gives me an amount that it specifically grows through or grows to at a specific time, so this would be my P of T, where that specific T is equal to 5. So again, our template was P of T equals P sub 0 times e to the KT. So if I just use that and replace what I have, the only unknown I should have left is the K, which is technically what the first part wants us to solve for. So for part A, I'm going to go ahead and just replace the P of T with its value, 2,504.65 cents, being equal to the original investment, which was 2,000, times e to the K, which I don't know, then times the T, which I do know for this specific amount was 5. So we'll solve this similar to how we had to solve the last time there was some variable up in the exponent, first by moving the coefficient over, which if I go ahead and divide that out, let's see what that turns into. Comes out as a 1.25233. I'll go ahead and go as many decimals out as my calculator is showing me, and that gives me e to the k times 5. I'm going to write that as 5k because having a coefficient in front of the k makes more sense to me. So at this point, just like we did before, we'll take advantage of the inverse of an e function is the natural log function, so those two will cancel each other out. So really all I'd have to do is divide by 5 after that, and that will give me my K value, or the interest rate, to be the natural log of that number, then divided by 5. So it gives us the k to be 0.045. So part B now wants us to actually set up what is that growth function. So that's going to be replace the P of t equals, still use the initial investment, then times e to the k, which I just solved for, 0.045, and then t. So notice I replaced the t and the amount, so kind of the last two things the problem gave me to be able to come up with my general formula. So the next two parts will basically just be some applications of what we just got. So once again, that equation we had, just so we have it on this screen, was P of t was equal to the 2,000 e to the k that we solved for, 0.045 t. So what will the balance be after 10 years? So for part C, it's really just evaluate what is P of 10. And so if I were to go through and compute that out, it's going to be whatever 2,000 times e to the 0.045 times 10 would turn into. So if we go ahead and just type that in, it gives me a value that's approximately equal to 3,136 and maybe about 62 cents if we were to round. So since this is in terms of money, we can use a money symbol for our final result. So again, that would be an approximation just because I have done a little bit of rounding to make that happen, but technically we can't go beyond pennies anyway, so there we go. The next part is going to be how long will it take for that to double. So that kind of is in a way telling me that when it doubles it should be at 4,000, and that would be equal to 2,000 e to the kt, which again the k value is not going to change from after we solve it. It's going to be the same k the entire time through the problem. But for this one, we would do a similar step, divide the 2,000 over, just like we did to solve for k before. This would turn into just a plain 2 on the left side, equaling e to the 0.045. And just like before, to cancel the e, I'd introduce a natural log to both sides because that is the inverse of e. That then should leave me just a 0.045t that I could divide that 0.045 off of. And so the t in this case comes back as whatever the natural log of 2 is divided by 0.045. And for this, I'll just round it to the tenths place. Comes out approximately 15.4. And again, the time unit for these problems is in terms of years. So just make sure that you include the label of years. So one thing that is kind of nice with that last part of that problem, which was the how long would it take for it to double, is there is actually somewhat of a shortcut. We can actually take advantage of this relationship between k and t, which basically will always be the product of those two things would always just equal the natural log of 2. So depending on which thing I wanted to solve for, if I wanted to solve for the actual rate or the actual time, I would be able to plug into one of these two forms, either the k isolated or the t isolated. So notice that it really does not in any way, shape, or form have any relationship or depend upon whatever the original investment is to figure out how much it would double. So I could invest $1 or $1 million, and the amount of time it would take to double based upon the situation that we had is going to come down to basically one of these two things, depending on how long either it gave you for the time or if it gave you a growth rate. But notice I have the ability to solve for one if I know the other, depending on, again, how the problem was presented. So let's go ahead and maybe try out an example of this. So in this case, it says the population of the Philippines is now doubling every 37.7 years. So that would be representing a time, or a t. So that should allow me to figure out the growth rate k by just doing the k equaling the natural log of 2 being divided by whatever the time was, which in this case is 37.7. So if I took the time to actually type in the natural log of 2 and then divide by 37.7, it gives me a value of approximately 'the k for that one came out approximately 0.0184. And if we wanted to convert that to a percent, it would just become 1.84% if we really wanted to, but for this problem, just leave it in the decimal format. Don't worry about doing this switch to percent unless the problem specifically said something like answer as a percent. Part B, it says the population of Meridian had a growth rate of 5.54%, so that one is written as a percent. So I first want to think of it as a decimal, so move the decimal 2 places to the left, 0.0554. And it says how many years after that would it take for it to double. So once again, it's going to be solving for a t, and in this case it would be the natural log of 2, just because it's talking about doubling over, in this case, the k value, so 0.0554. And for this one, typing that in, I get approximately 12.5 years. Now it didn't ask for what year would it be double, it just said how many years after, so I didn't have to worry about doing like 2017 plus that number, because it was really just talking about the years after. So in addition to be able to doing that kind of idea of doubling, we could even I guess apply it to really tripling if I wanted to. It would just have a 3 inside instead of a 2. But we can also apply it going the other direction, and so instead of being a growth rate, now we can actually say it's a decay rate, or it's losing an amount. So for this one, what we would oftentimes call this, or a lot of the application problems for something like this, is what's called the half-life. So notice a lot of questions as you get into these types will involve that phrase half-life. And as you can see, the formulas themselves are almost identical to what we had from earlier, except instead of a 2 inside of the natural log, now it's actually a 1/2. So notice half-life has 1/2 inside, doubling had a 2 inside. Hopefully that's not too unreasonable to expect. So if I were to maybe bring up the idea of how long would it take to triple, I would just expect there to be a natural log of 3. Or if I said quadruple, it would be natural log of 4. So notice the number inside the log really just kind of corresponds with what am I having happen. Now, since this is a decay rate, the expectation, if I were to do maybe the solving for the k, or the one in the middle, is I expect that k to come back less than 0. In other words, I expect that to come back as a negative number if this truly is a decay relationship, or a decay, I guess, type concept. So anyway, I just wanted to kind of point out that there is a way that we can apply this and go the other direction. It doesn't only apply to the growth models, it also applies to these decay models. So anyway, let's go ahead and work through an example with this. This one is giving us specifically an element carbon-14 that has a half-life of 5,750 years. So since that gave me a time, hopefully that's reasonable, that I should be able to solve for the k using one of those formulas from earlier. So it's going to be the natural log of 1/2 that I would then divide by the 5,750. And if I type that into the calculator, this turns into a negative result, which is good because this should be decaying if it's losing or if it has a half-life. So this would be a negative 0.000121 if I were to round it. On a calculator every once in a while, sometimes it might give you something like an e to a -4. That really just means move your decimal 4 places to the left, which is why there would be 3 extra zeros in front of the 1. But again, still keep the negative sign that's in front. So anywho, that should now allow us to set up our expression here for what we have. In this case, the question is actually saying it's lost 22.3%, but when it comes to like our format, the P of t equaling our P initial, or p sub 0, times e to the kt. We've solved for the k. It didn't really give me how much I started with, and it didn't really, or in this case, it's not really telling me how much is left, it's just telling me how much I've lost. Well, if we think of how things should work, when something first originates, it should have 100% of whatever this is. So that should be 100 as like the p sub 0. And then I've lost 22.3, so if I started with 100 and I said I've lost 22.3, that really should tell me that I have 77.7% left. And instead of worrying about converting this percent, since it's actually more talking about an amount, I could say, like, maybe hypothetically, if I started with 100, then my end amount would just be there's 77.7 now left. So I'm going to take advantage of that concept and just say, well, 77.7 should equal, starting with 100, and then e to whatever our k was, which we just solved for, the negative 0.000121, and then t. So I would now start pretty much the same as most of the other solving ones, divide the coefficient over. In this scenario, it actually kind of turns it into a decimal version, or it's like I converted from percent to decimal. But that now gives me e to the negative 0.000121t still on the right side. To cancel the e, I would now introduce the natural log. That way, again, because of that inverse relationship, they cancel out. And then it would just be divide by that negative 0.000121. That's the coefficient in front of that t. So everything from here is now just typing into the calculator. So I'm going to go ahead and grab one, natural log of 0.777, then divided by a negative 0.000121 gives me a t value in this case of 2085.25, and this is representing a time in years, so it would be years old. So this specific scroll happened to be, or this linen wrapping, I guess is how they've really phrased that, is approximately 2085 years old, just a little bit more than that. Alright, so we'll move on to our last example, at least as far as models are concerned. So this is kind of a situation that should be relatively reasonable, and the fact that we have some sort of population that can only max out at a specific value. So it's kind of like the idea of there's only so many people that could potentially fit maybe like in a room, that eventually we would get to a point that the population growth would have to kind of slow down, or it would kind of reach a little bit of a I don't know, it can't grow anymore, if you want to think of it that way. So in other words, when we have a limited growth model, in other words, something that we know where there is a maximum capacity, we would utilize something like this. So notice there still is kind of that idea of times e to a power, even though it's an e to the negative kt, which seems like that should be a decay model, because that power is in the denominator. The negative power on the bottom, really you could kind of picture like it would be able to be interpreted as like a positive power in the numerator, which is why this still would be technically a growth model. This is what is called a logistic function, and as far as the values are concerned, the a value that's in the numerator is essentially going to be whatever that maximum capacity or whatever the limiting value actually is. And as you approach infinity for the t, in other words, as I plug in the most giant number possible for our time unit, our end result would basically get closer and closer and closer to that a value, which is what we would call graphically a horizontal asymptote for the graph. So for this particular, I guess, setup, really the variables that we need to know are what is the a and potentially what is the rate. And then we would leave the t, and more than likely we could solve for the starting population by just plugging in 0 for that, which should just leave me the a value over whatever 1 more than b is. So I could utilize, if I knew what the starting population is, I could use that to my advantage to try and solve for the b that would be in front. So most of the time these functions are going to be things that will be provided for you. And in fact, in our class, we're going to provide you anytime this type of formula is or if we're asking you to use something like this logistic function, we would provide the formula for you. You wouldn't have to build it like we had to do with the exponential growth ones before. So ultimately, these types of questions, when they're presented, they really are just going to turn into kind of a calculator exercise more than anything. But just to kind of give you a little bit of context as to what would be a scenario where this would be a model that would be reasonable, ultimately this would be one possible thing. The idea of filling up a room, like I presented earlier, would be another possible example where there is a true max occupancy, so we could kind of figure out how much population would be somewhere if we had a specific growth rate that was presented. Anyway, again, these problems, you won't have to do any of the building. It's more just take the function and plug things in. So notice they've provided us with what the P of t is, and it just wants us to evaluate some specific numbers. What is the time at 0, or sorry, what is the population at 0, after 1 month, after 5 months, after 10 months, 15 months, 20 months. So it's really just a bunch of plug-in numbers. So if I plug in 0, it should give me the how much I started with, which they actually told me how much I started with. That's going to be the 400 fish. If I plug in 1 to that function, plugging in 1, it comes back 50, or sorry, not 50, but 519.5. Well, I can't really have 0.5 of a fish, so I'm just going to round down each time because, well, there's no such things as a fraction of a fish. So 519 total fish after 1 month. After 5 months, if I plug in 5 where I see the t in that function, I guess maybe I should have pointed this out. If you don't have the ability to make the fraction look like what it is on the screen on your calculator, you would want to make sure that you're throwing some extra parentheses around the denominator so that it does that portion before it actually does the division. So just wanted to kind of point that out. I guess another thing to maybe point out about the formula is it did tell us that the lake has kind of a limiting value of there can't be more than 2,500 fish in there. Otherwise they'd be right up next to each other and wouldn't actually be able to do anything, nor would there be maybe enough food for that to actually, I guess, allow for that or any more than that number of fish to actually exist. But anyway, that's kind of again, the context of this. You can read through the entire thing, but ultimately it was just let's utilize the formula that they provided for us and understand the idea of as time goes, the amount of fish is going to grow, but eventually it's going to kind of slow down as I get closer and closer to, I guess, infinity for t. And in this case, I'm only topping out at 20 months, but we may get relatively close to that 2,500 mark even by that point. But anyway, let's go ahead and plug in 5 for the next one since we still have some more numbers to do. So if I plug in 5 and simplify, it looks like it turns into 1,213 fish. Move on to the next number, plug in 10. If I go ahead and plug in 10, that looks like it turns into 2,060 almost, actually round down, 2,059 fish for that month. So notice we are getting closer to that 2,500. After 15 months, it turns into 2,396. And we'll go ahead and plug in our last number, P of 20. And that gives me approximately 2,478, so 2,478 fish at that point. So it kind of seems like after almost 2 years, the lake would kind of be at its max capacity of fish before maybe they start slowing down in how fast it's actually growing. So if I were to go to like maybe 25, I would kind of expect it to still be relatively close to what it was at 20 because we're getting closer and closer to that 2,500. So anyway, this is just a different kind of model that still is the idea of growth, but now having a limitation on it, which if you think in real world context, there probably are quite a few situations such as this one where I can't just continue to grow infinitely, that eventually I reach like a capacity of some particular scenario. In this case, they were talking about the scenario of a lake can only have so many fish before it really runs out of food. So anyway, hopefully this video has been helpful when it comes to understanding kind of the application of the either exponential growth or exponential decay. Key takeaway from that concept is a growth model is going to have a rate that comes back positive, whereas a decay model will have a rate that comes back negative. When it comes to the setting up and the solving, really there's no big difference between it. But if you were to look at the graph, it definitely would switch from increasing for a growth model to decreasing for a decay model. And so the most common application of the decay idea for you guys will likely be just dealing with things like a half-life of some particular thing. In this case, they were talking about the half-life of carbon specifically. And then you can use that idea to potentially set up for like how old something maybe really was. Anywho, as always, if you have questions as you're working through your assignment, we can always work through them together as a class. So feel free to fire away with questions as they pop up. But I appreciate you guys taking the time watching this video, and we'll go ahead and catch you next time.